live. Okay. Yeah. So for those who are not here. All right. So there's a PDF at the top of your unit, and it says thermodynamic data. And that is going to be all the numbers for our homework. We're going to use all of the enthalpies, free energies, and entropies from this table. So if you're doing homework and you're like, what is the value? If it's not in the homework, these are the values we're going to use. Okay, so far, so good? All right, so just like they sprinkled in a little bit of acid and base throughout the unit, they also moved the entropy and free energy section to the very end of the unit and then tied it in with electrochem. And there's a couple different reasons that they did that. If you remember from last year, the delta G is the available energy in a system. We call it Gibbs free energy. And it is based upon the delta H and the temperature and entropy. And it is entropy that we're going to be talking about today. Remember, entropy is chaos. It is randomness. It is molecular disorder. And for reasons that I don't want to get into now, but you are welcome to listen to Veritasium and he'll explain it. If you just do Veritasium entropy, he'll explain all that stuff, or Veritasium energy solar. But anyway, he's got a video that explains the relationship of entropy and energy and how the universe tends towards, or why the universe tends towards an increasing entropy. For this unit, just understand that when we talk about thermodynamically favored systems increase their entropy. Okay? And that's the lingo we're going to use. Thermodynamically favored, sometimes we'll say product favored, sometimes we'll say reactant favored. But when we're talking about a system that is thermodynamically favored, that is an increase in entropy. So overall, there's a negative sign right here for math that we'll deal with in a second. But the reason they pushed this all the way back to the end is delta G can be calculated with electrical energy. And electrical energy can give us delta G. Additionally, delta G can be found with equilibrium, and equilibrium can be found with delta G. So pretty much every reaction that happens has some sort of energy relationship. So since it did that, the AP said decades ago, you know, they really should know equilibrium before they learn Gibbs free energy. And they need to know Gibbs free energy before they can do electrochemistry. So the first half of Unit 9 is adding entropy to the enthalpy you learned in Unit 4. I think Unit 4? I think that was Unit 4. No, Unit 6? I just have to go over it and figure it out. Unit 6. Okay, so we're adding entropy to the enthalpy that we learned in Unit 6 to get a free energy value. And once we're comfortable with free energy, we're going to learn electrochem, and we're going to tie entropy and enthalpy together to get free energy, and free energy to equilibrium, and free energy to electrochem. This is going to be a pretty quick day, by the way, because we're just going to focus on entropy today. But any questions before we get into it? Okay, so 9.1.2 is just entropy. There's a couple really important things we need to talk about entropy. Most important is that entropy is a state function, meaning if we look at the beginning and look at the end, it doesn't matter how we get there. Just like enthalpy, you can go from A to Z in 6 steps or in 1 step. It's going to have, as long as you start at the same place and end at the same place, the process is going to have the same overall entropy change. Now, the reason that's important is because we can then use Hess's law for entropy, just like we used Hess's law for enthalpy. The change in entropy is equal to where we ended minus where we started. Okay. Remember Hess's law? Doesn't matter how you get from A to B in 1 step or 30 steps, the overall energy change is going to be the same. So we can apply that to entropy as well because it's a state function. So the change in entropy is just going to be the delta S of the products minus the delta S of the reactants. In other words, where we are minus where we started. Delta H works exactly the same way because it's also a state function, delta H of the products minus delta H of the reactants. And we're also going to find out that free energy is also a state function, so delta G, the delta G of the products minus the delta G of the reactants will also give us, actually let's just get rid of all the deltas, G products minus G reactants, H products minus H reactants. So the state of the products minus the state of the reactants gives us our deltas, our changes. Okay, state functions do that. All right, give me a thumbs up if you're clear with that. Wave your hand around if you have any questions at all. Okay, so like we learned last year, entropy is a measure of disorder or randomness, and a positive delta S is an increase in entropy. In other words, a positive delta S means there is more entropy in the products than there was in the reactants. Also very important in entropy, there are no negative entropy values. There are no negative entropy values. In fact, there is no place in the universe that we know of where entropy is zero. That's the third law of thermodynamics. Basically, it says there's an absolute zero value and you can't get to it. We have got down to billionths, trillionths of a Kelvin where the delta S is extremely small, but we can never get to, or where the S is extremely small, but we can never get to zero. We can have a negative delta S, but we can't have an S that is zero. So far, so good. Another thing, and you can blame this on the physicists, the units, I mentioned this last year too, the units of delta G are kilojoules per mole. The units of delta H are kilojoules per mole, but the unit of entropy is joules per mole Kelvin. Which means, if you ever have to use your entropy in the Gibbs free energy equation, you need to turn your entropy value into kilojoules per mole Kelvin. Why is that, Mr. Byers? Because the physicists only use standard units. Chemists use things like atmospheres and kilojoules and grams, which are not standard units. The standard units are actually the Pascal and the, what is the middle one? Oh, liter? Yeah, we use liters, they use cubic meters, and we use grams, they use kilograms. So physicists always have to use standard units. And when you use standard units, the entropy value is going to be in joules per mole Kelvin, not kilojoules. Because they use entropy too. All right. If you're with me so far, give me a thumbs up. Okay. So, takeaways. There is no zero S, no negative S, but there can be a zero delta S, and there can be a zero or negative delta S. And additionally, entropy is going to have the value of joules per mole Kelvin, and enthalpy and free energy will be kilojoules. Okay, so the first law of thermodynamics states that energy contained within the universe is constant. Basically, if energy is created or destroyed, something else has to donate or take away. So if the overall energy change is positive in the system, it's got to be negative in the surroundings. If the overall energy is negative in the system, it's going to be positive in the surroundings. It's got to go somewhere. Okay. Second law of thermodynamics is entropy of this universe is constantly increasing. You really want to bake a physicist's noggin? Ask him for the mechanism of increasing entropy. It's like, what's the mechanism for gravity? We have a mechanism for gravity. What's the mechanism for force? We have a mechanism for force. What's the mechanism for increasing entropy? God just made it that way. There's no mechanism for it. It's just that's what happens. By the way, again, a law is not something you can't break. A law is a description of natural phenomena. And what we find is the natural phenomena is the entropy of the universe is constantly increasing. Practically what that means is if your refrigerator drops the energy inside the refrigerator by 100 joules, it's going to increase the energy outside the refrigerator by 100 plus N joules. It's not going to be a 1-to-1 ratio. If your car engine was perfectly 100% efficient and it increased your kinetic energy by 100 joules, the fuel that would require that would be more than 100 joules to change that energy over, the energy conversion. There is no perfect energy conversions in reality. In math, yeah, okay. So things that increase, processes that increase entropy, melting from a solid to a liquid is going to increase the entropy. It's like, if you're trying to figure out if entropy is going to increase, imagine painting a molecule and then coming back to it and trying to locate that painted molecule. Pretty easy with a solid. You're like, there it is, and it's just moved a tiny bit. It's just vibrating a little bit. With a liquid, it's like, okay, it was there. Oh, now it's over there. And with a gas, it was there. Now it's way over there. Okay. So if you can imagine having to track a molecule, if it's hard to track a molecule, entropy went up. Vaporization, liquid gas, same thing. Reactions where the products are in the same phase as the reactants but contain more particles. So increasing entropy is a phase change towards gas and more particles being present. Also, making solutions, because our solid over here, you know where the ions are. Like, there's my positive ions, there's my negative ions. It's not too complicated, they're right there. But then when they dissolve, those ions just end up all over the place. They're like, oh, where are they now? I don't know, they're floating all over with the water molecules. Speeding molecules up increases their entropy. That should make sense. Which has more entropy? 10 toddlers asleep or 10 toddlers not asleep? 10 toddlers not asleep have a lot more entropy. And of course, if you increase the volume of a gas, you allow the molecules to move more. That will also increase the entropy. Okay. Are we good? Give me a thumbs up if you're comfortable with what we're talking about so far. All right, so there's all examples. Okay, here's an example where we have 4 liquids go to 6, 18, 28, 29 gases. So entropy increases a lot because not only are we going from liquids to a gas, which increases entropy, we're also going from 4 molecules to, what is it, 28 molecules? That's an increase in entropy. Same number of molecules going to a more energetic phase will increase entropy. Same number of molecules, same phase going to more molecules will also increase our entropy. All right, so this is again phase change. You've seen these before. Gases, more entropy. Solids, less entropy. These are distributions. Higher temperature, more entropy. Lower temperature, less entropy. I think possibly. Okay, and again, we're going to apply Hess's law to entropy, where it's products minus reactants. These are the sums of, meaning you're going to take all of the entropies of all the products minus all the entropies of all the reactants, and we're going to use the stoichiometric coefficients in there as well. We're going to practice right now. Okay, so take a look at this. Calculate the delta S. Before we calculate it, we want to estimate it. Does it appear to increase or decrease in entropy? Decrease, because we're going from 3 gases to 1 gas. 1 gas has less entropy than 3 gases, so it appears that our entropy is going to decrease, which would give us a negative entropy. Now, go open up that thermodynamic data and find nitrogen and oxygen and N2O4, and then calculate, using Hess's law, what the entropy value is. I will wait for you. oil. Have to oil the valves before and after using. Made in America, in New York. Woot woot. Okay, are we good? What was the energy value that the table gave you for N2O4 gas?
304.29.
304 point what?
29.
3. And what was the nitrogen value that it gave you in gas?
191.64.
191.7. And what was the oxygen value it gave you for gas?
205.13.
205.1. So doing the arithmetic, 304.3 minus the sum of 191.7 plus 2 205s, what does it appear to be our entropy change?
Negative 297. Well, 3 sig figs, right?
Well, 4 because we have decimal.
0.6.
0.6. And the unit here is going to be the joule per mole Kelvin. Molk. The joule per mole Kelvin. Are you comfortable with this calculation? Okay. The pitfalls you got to watch out for, 2 of them. First of all, make sure you take the stoichiometric coefficients and put them in there. Second one is this. It very rarely happens on the AP test. Because it's kind of one of those ticky-tack, let's trick the kids kind of things. But the state is important. A gaseous, for water molecule is a great example. Gaseous water has a much higher entropy than liquid water, has a much higher entropy than solid water. So the state is important. I don't think it's ever going to come up on the AP, but just in case. If you are ever given, again, stick with water, if you were ever given H2O liquid and the equation had H2O gas in it, you would need the conversion from H2O liquid to H2O gas. You would need to do that first. Don't think it's ever going to happen, but just in case, keep track of your states. Give me a thumbs up if you're ready to move forward. Move on. Okay. Go away, little button. There you go. Yeah, I told you it was going to be short. We're pretty much done. That value, NiO, nickel 2 oxide, is missing in the table, but it's 38.0 kilojoules per Kelvin. All right, and did I have any notes on which ones I wanted to do? No, I didn't. Okay, you're just going to work. All right. If you have any questions, now would be a good time to ask. Otherwise, I'm going to let you work on your assignment. All right. No notes. Just go right to it. And stream. And